Acidic nature of carboxylic acids. Carboxylic acids are by far the most acidic amongst all the organic compounds that we have studied so far. However, these carboxylic acids are much weaker acids if you compare with the mineral acids like nitric acid, sulfuric acid, or the hydrochloric acid. Carboxylic acid, when it releases this acidic proton, you get the carboxylate ion or CO negative here, and it is the conjugate base of this acid. And we know the strength of an acid depends on the stability of a conjugate base. If the conjugate base is stable, the acid will be more stronger. Okay, so same concept here we can apply. That means all those factors which actually increase the stability of a conjugate base will increase the strength of the carboxylic acid. Here in the carboxylate ion here, it is the resonance which makes it the stronger acid among all the organic acids. Correct? You can see here in the carboxylate ion there can be the resonance. This electron pair goes down and this will go over here, right? And then you can draw one more resonating structure for this carboxylate ion that will be like this, RCO negative here, and now you get a double bond with this particular oxygen. And this electron pair can go back here and this will go here, and so you get the first structure back. That means due to the resonance in the carboxylate ion, it is very much stable, right? So it is the resonance here in the CO negative part that makes it stable. The negative charge on the oxygen goes to the another oxygen, right? And due to this resonance, the molecule becomes stable. The conjugate base is very much stable. That's why this acid is more stronger acid among all the organic acids. This is more acidic, even the phenols. So what are the factors that can increase or decrease the strength of an acid? We know that anything that can actually increase the stability of a conjugate base, right? I'm going to repeat it. Any factor that will increase the stability, if we can increase the stability of a conjugate base, then acid will be more stronger, correct? So the factors that actually increase the stability of what? Stability of the conjugate base. Okay, stability of the conjugate base. If the stability of the conjugate base will increase, the acidic strength is going to increase. Okay, acidic strength will also increase. And we can compare the acidic strength of the carboxylic acids in terms of their dissociation constant. In the aqueous solution, the carboxylic acids ionize and it exists in dynamic equilibrium with the carboxylate ion and the hydrogen ion. Okay, this is our carboxylate ion and this is the hydrogen ion. So now this is under equilibrium with this system. And when you apply the equilibrium constant here, so we can see equilibrium constant will be concentration of the hydrogen ion and the concentration of the carboxylate ion divided by the concentration of the water and the carboxylic acid. And you can rearrange it here, concentration of water, which is the solvent here, and then you get another constant which is called as an dissociation constant of the acid. Okay, Ka value. So Ka is actually what? It is a dissociation constant. So higher Ka value here means what? It means that the acid is stronger. Correct? If you have two different acids, suppose you got the acid A and you got the acid B, right? So let's suppose here the dissociation constant of the the acid A is, let's say it is let's say 17.5 times 10 power minus 5. Okay, this is the dissociation constant of the A. And if you take the acid B and its dissociation constant is, let's say, 1.75 times 10 to the power negative 5, then we can say that A here is more stronger than the B because the dissociation constant of A is higher. So higher Ka value, higher dissociation constant of an acid means it is a stronger acid. Okay, so higher value means stronger acid, lower Ka value means weaker acid. You can also we often compare the acidic strength okay, of the different acids in terms of the pKa value, right? So pKa value, what is this pKa value? pK is, it's the negative logarithm of this K value, this dissociation constant, negative log K. This is what you call as a, the pKa value. And this, when you compare the acidic strength in terms of the pK value, it becomes much more easier to compare the strengths, because you get certain, numerical values here, okay? Some simple numerical values. For example, if you find what will be the pKa value here, pKa value for this acid A, which has a K value, 10.5 times 17.5 times 10 power negative 5. If you find this pKa value here, it will come out to be, let's say it will be around 3.75, okay? And if you compare with the B, what will be the pKa value of the B? So pKa value of the B will be around 4.76, okay? It will be 4.76. So higher pKa value actually means the weaker acid, okay? Higher pKa value means weaker acid, okay? So I'm going to write it here. The pKa higher value means it is the weaker acid, okay? The lower pKa value means it's a stronger acid. Now coming to the factors, what can actually increase the acidic strength? If you have an acid, how you can increase the strength of an acid. As I said, all those factors that will actually stabilize this conjugate base will actually increase the strength of an acid. If you have a carboxylic acid or COH, and if you dissociate the proton here, then what do you get? You get RCO negative here. And now all those factors that will actually stabilize this conjugate base will increase the strength of an acid. So if you have an electron withdrawing group, if you attach an electron withdrawing group, that something that can withdraw the electrons, that can decrease this negative charge on the carboxylate ion. That means all those electron withdrawing groups, they will stabilize the conjugate base, which means that the acidic strength will increase. Correct? So that means if you have an electron withdrawing group, if you attach an electron withdrawing group, that's going to increase, right? It's going to increase the acidic strength. Okay? Acidic strength. So electron withdrawing group will increase the acidic strength because it will stabilize the conjugate base. And electron releasing groups or electron donating groups, they will donate electrons, so that because of that, the negative charge will increase. Correct? The negative charge will increase, so it will make it unstable. Correct? So when negative charge increases, it will make it unstable, which means that electron releasing groups, or you can see electron donating groups, they will decrease the acidic strength. Okay, it will decrease the acidic strength. So let me compare here few examples. Okay, if you got the CH3 C double bond OH, now you compare it with this is an acetic acid, and if you compare it with, let's say you got here the CH2 C double bond OH here, and let's say this is the chlorine. As we know that this methyl group here, CH3, it is electron releasing. It has a plus I effect, positive inductive effect. So that means this is electron releasing group. It is electron, releasing group. So that means it will actually donate more electrons. So the conjugate base will be, it will be less stable. So that means this will decrease the acidic strength. It's going to decrease the acidic strength because you have here a electron releasing group. Now you have a chlorine. In this case, chlorine is going to withdraw electrons from this, so it will take the electrons away because it has a negative I effect. So negative I effect means it will withdraw the electrons. Is an actually electron withdrawing group, so therefore it will increase the acidic strength. It's going to increase the acidic strength, which means that here the B is more acidic than the A. Okay, the B is more acidic than the A. This one is more acidic than the A. Let's take few more examples. You can see all these groups here, CF3, chlorine with 3 fluorine atoms, NO2, cyanide, halogens, iodine here, and the phenyl ring. All these are actually electron, withdrawing groups. Okay, they're going to withdraw the electrons from the carboxylate ion. So if you attach any of these groups, to the carboxylate ion, all these groups, they will stabilize the they're gonna stabilize the conjugate base because they will withdraw the electrons from the carboxylate ion. So that means they will increase the acidic strength. Okay, so nitro group, it's going to withdraw the electrons, so it's an electron withdrawing, so it will stabilize this conjugate base. That means it will make it more acidic. But CF3 is the most. So when you have a carbon with 3 fluorine atoms, it can withdraw electrons. It has fluorine, which is the most electronegative atom. If you have 3 fluorine atoms, so it can withdraw electrons a lot from this carboxylate ion. That will increase its stability. That means it will be the most acidic. Okay, and then nitro, all these groups actually they withdraw electrons, but the CF3 has a high highest electron withdrawing effect. Then the nitro, then the cyanide, then fluorine, chlorine, bromine, iodine, and phenyl. See, interesting one is phenyl. Okay, if you attach a phenyl, it's also going to withdraw the electrons. Why will it withdraw the electrons? Let's just check it out, right? How it can withdraw the electrons. Basically, the phenyl ring, the benzene ring that we have here, it has an sp2 hybridized carbon, right? This particular carbon is sp2 hybridized. Okay, and we know that sp2 hybridized carbon is more electronegative than an sp3, isn't it? So it's going to withdraw the electrons from the from this particular carboxylate ion. So it has a little bit electron withdrawing effect. So it will take the electrons away from the carboxylate ion. So that means it will increase the acidic strength. Okay, so that means if you compare the phenyl ring here, you take aliphatic carboxylic acid, let's say you got the CO negative and you have here the CH3. This aromatic one is more acidic than this one because here you have an electron releasing group. Okay, this is electron releasing group, so it will release the electrons, so that will make it less acidic. But phenyl ring, benzene ring that we have here, it's an sp2 hybridized carbon. It's going to withdraw the electrons because of its little more acidic nature, more electronegativity. sp2 hybridized carbon is more electronegative atom than sp3. Here in this case it is an sp3. So if you compare these two, then this one sp3 is electron releasing, sp2 is electron withdrawing. So it will take the electrons a little bit away from it, making it more acidic. Okay, so that means the aromatic carboxylic acid is actually more acidic among all the aliphatic carboxylic acids. Okay, carboxylic acid, which is aromatic here, is more acidic than any of the aliphatic because you have here an alkyl. An alkyl group, R group, is always electron releasing group, right? So that means this one is more acidic among the these. If you compare the aromatic one with the aliphatic, aromatic should be more acidic. Now if you attach an electron releasing group, right, electron releasing group, that will decrease the acidic strength. So let's take a couple of examples here. For example, if you have a formic acid, an acetic acid, which is a more acidic, okay, which is more acidic. Formic acid is more stronger than the acetic acid. Why? Because here you have a hydrogen, and hydrogen cannot donate electrons. Here you got a methyl group. It has a positive effect, so it is electron releasing group. So it will donate electrons, so it is electron donating groups. So that will decrease the stability of the conjugate base. That will decrease the acidic strength. So that's why the formic acid is more stronger acid than the acetic acid. And if you compare any of the aliphatic, as I said, any of the aliphatic acid with the aromatic one, right? So if you have an aromatic acid, C double bond to OH, and if you compare with the aliphatic ones, aromatic is more acidic than the aliphatic, than any of the, whether it is methyl, ethyl, whatever it is. Okay, why? Because here you have an sp2 hybridized carbon. Okay, you have an sp2 hybridized carbon. Here you have an sp3 hybridized carbon. But if you compare the this benzoic acid, aromatic or carboxylic acid, with the formic acid, then again the formic acid here is more acidic than this one. Okay, so formic acid is more than the aromatic, and aromatics are actually more acidic than any of the aliphatic carboxylic acids. Now let's take this example here. You got a COH, and this is an ethyl group, C2 alkyl chain. This is a methyl one, and here we can say then this CH3, it has a plus I effect, positive I effect. This ethyl group also has a positive I effect, but since ethyl is more electron donor, so that means it will be less acidic than the methyl one, right? So methyl has a lesser electron donation power than ethyl group. So here, the ethyl group will donate electrons more, so that will make it very much less, stable, okay? Because electron releasing groups decrease the acidic nature, right? So this one has a more electron donation power than the methyl. And now if you have a benzene ring here attached to this one, CH2, as I said, this benzene ring, it is slightly more, it has a sp2 hybridized carbon which will, actually withdraw the electrons. So that means it will make it more acidic than this one, okay, because this has a negative I effect, okay. This phenyl ring has a negative I effect, so it will pull the electrons a little bit, so increases the acidic strength slightly. And now you got here a C6H5COH, then why it is more? Because here the C6H5 is directly attached to the carboxylic acid. Here in this case it is the CH2 which is attached to the benzene, and then you have a COH. Let me draw the structure here to explain it more clearly. This is our CH2, and then you got the C double bond OH, and then you have a benzene ring, you have a phenyl ring here, okay. And now this phenyl ring, it will pull the electrons from here. The distance is more in this case, so the effect will be less. But right now here in this case, you got a COH group and you have a benzene ring attached directly to it, so it's more closer to the carboxylic ion. It will pull electrons more, so the effect will be more. That means this is more acidic than this one. Now what about the aromatic rings? If you do some substitution. Before we take this ortho effect, what actually it is, let me give you a brief idea. If you do any kind of a substitution to the aromatic ring, so what will be the effect of the group that you attach to the carboxylic acid? If you attach any group here, what will be the acidic strength? Will it increase or decrease? It actually depends whether it is electron releasing or is it electron withdrawing, okay. So if it is electron releasing group or if it is electron donating group, right? So electron donating groups, we have learned that they decrease the acidic strength, correct? So electron releasing group will decrease the acidic strength here, okay. And if it is electron withdrawing group, if it withdraws electrons from it, then it will increase the acidic nature. So that means in simple case, let me take one simple example here. This is the COH, and if you have here, let's say you got here a methyl group attached to it, CH3, and you got another molecule where you have a COH, and then you have here, in this case you got the nitro group. Now let's say this is the first one, this is the second one. Which is more acidic? We know that nitro group is electron withdrawing group and this is electron releasing group, okay. Electron withdrawing group is going to make it more acidic, so that means B will be more acidic than A, right? Because electron withdrawing groups, they will pull the electrons, make the conjugate base stable, therefore it will be more acidic than the methyl, because it is electron releasing group. Electron donating or electron releasing group, they will decrease the acidic strength. But if the same group is now attached at the ortho position, okay, you got here a COH group and you have here now a group attached at the ortho position, right? Now whatever is the nature of the group, irrespective of the nature of the group, it will actually increase the acidic nature, whether it is electron releasing or electron withdrawing group. In all the cases, whether it is electron releasing group or is it electron withdrawing group, in both cases it will actually increase the acidic nature. Very interesting here, right? But remember, this is only at the ortho position, not at the meta and the para, correct? Not at the meta and the para. Meta and the para, so you're going to remember this thing. But if the group is present at the ortho position, we know that, if you have a COH group, there are two ortho positions, over here or over here. So if the group is present here or here, whether it is electron releasing or withdrawing group, in both cases it will actually increase the acidic nature. This is what you call as an ortho effect. So if you do a substitution at the ortho group, at the ortho position to the benzoic acid, it will increase the acidic nature. Why? Why should it increase the acidic nature? Okay, it's because, as I said, the stability of the conjugate base actually determines everything, determines the acidic nature, right? So here, due to the steric, repulsion, steric, inhibitions here, right, between the group at the ortho position and the COH, due to the bulky size of the COH, and if you attach one more group at the ortho position, there will be some steric repulsions, right? Okay, some repulsions due to the size. Okay, so they will repel each other. That will force this hydrogen to go out of the COH group. Correct? So when you have here a group attached to the ortho position, because of the more steric hindrance, this COH group will release the proton, and therefore what you get? You get a conjugate base like this, CO negative. Okay, CO negative, and then you have here a group attached at the ortho position. Now if you compare the two here, right, when hydrogen is released, the size is, the size of the group decreases here. Okay, so now you have a less repulsion. That means this conjugate base is more stable, right? So now the electronic effect here, you can see, this is not a dominant factor, right? Whether it is a electron releasing or is it a electron withdrawing group, it doesn't matter. What matters here? What is the dominating factor? It is the steric inhibition, steric repulsion, steric hindrances, we can say. So more steric hindrance here makes this molecule more acidic, because if it releases the proton, now it is it has a lesser repulsion, so that will make it more stable conjugate base. That's why it will increase the acidic nature. So whether you have electron donating group or you have electron withdrawing group, in all the cases it's going to increase the acidic nature. That's what you call as an ortho effect. Let's take a couple of more examples to understand it completely. We got here a carboxylic acid without any substitution. Let's say this is the compound A, and let me draw another molecule COH with now an OH group. Let's say the methyl group here, and you got here a third molecule COH, and now we have a methyl at the para position. Okay, which is the most, what will be the the acidic nature? As you can see here, you have a methyl group at the ortho position, so because of it is more repulsion, the B will be the most acidic among all the three. Okay, the B is most acidic, so the order will be like this: B is more acidic than A. Okay, and A is more acidic than B. Why? Because it is electron releasing group. It is electron releasing group. As I said, it doesn't matter whether it is electron releasing or withdrawing at the ortho position. So if you have a group at the ortho position, it will increase the acidic nature. So B in all the cases will be more acidic than A. Whether it is methyl, whether it is any other group, whether it is nitro group, whether it is cyanide, whether it is any other group, right? So B will be more, because the ortho substituted product will be more acidic than the the benzoic acid. And now you have a methyl group at the para position, so that means it will be the least acidic. So this is this is the least acidic. So this is the decreasing order of the acidic nature. Let's take one more example here. Now look at the three molecules here. We have a nitro substituted product. Okay, so as we discussed that a nitro group at the ortho position, okay, this will be the more acidic because because of the ortho effect. Correct? So among all the three, it is the B which is most acidic. Okay, now coming to the A and the C. A and C. Here the A is more acidic than the C. A will be more acidic than the C. Why so? Why A is more acidic? Why the para one is more acidic? Remember, always when you have to compare between the ortho and the para one and the meta position. So para, a group which is present at the para position, the effect is more. The effect of a group at the para position is more than at the meta position. Okay, means if you attach a group at the para position, it will show its effect more at the para position, whether it is electron releasing or withdrawing. In both cases, it will actually show its effect more at the para than meta. So now you got nitro, which is electron withdrawing group. So that will increase the acidic nature. Here also you have electron withdrawing group, but as I said, the group at the para position shows it is dominant effect. Okay, the para substitute product has a more effect. The group will show its effect more at para position than at the meta position. So that's why you have, the A1, the para substitute product, para nitrobenzoic acid is more acidic than the meta one. And the decreasing order of the acidic nature will be B, A, and the C. Let's take one more example to understand it completely. Here in this case, you can see we have a group at the ortho position. So the B will be more acidic than A. Okay, B is more acidic than A. And you got here the two methyl groups which are actually electron releasing groups. So this is electron releasing, this one is also electron releasing. Okay, electron releasing groups. And electron releasing groups, they decrease the acidic nature, right? So they decrease the acidic nature. Then in this case, we have a para position, a group at the para position. Here you got the methyl at the meta position. As I said, that a group shows its more effect when it is present at the para position than at the meta. Okay, so that means in this case, the group at the para position will decrease the acidic nature more than the meta position. Okay, here this one will decrease the acidic nature more than this one, which means that the C is more acidic than D. Okay, the C is more acidic than D. So this will be the decreasing order of the acidic nature of these four carboxylic acids. Hope you got the concept. Thanks for watching the video. Bye for now.